In this video, I'll be explaining generic functions. Generic functions allow you to write functions that work with multiple types of data. So what are generic functions? Generic functions are a type of function that allows multiple different data types to be used as a function parameter. Instead of providing a data type, as you normally would as a function parameter, you provide a trait. The function can then be used with any type of data that has an implementation of that trait. This can be done because traits exhibit behaviors. A generic function can then operate on the behavior defined on the trait instead of an explicit data type. Rust's type system guarantees that any type of data used as an argument to a generic function implements the trait required by the function. So, generic functions enable you to write a single function that can be applied to multiple types of data, as long as they implement a trait. And as a bonus, whenever a new type is introduced, it can be immediately used with an existing generic function without any modifications to the code. Now, before we jump into generics, I'm going to do a quick review of traits, since they are core to how generics work. Here we have a trait called move. The trait has a single function named move2, which takes an x and y values as coordinates to move to. We then have two structs. We have a snake and a grasshopper. And then we implement the move trait for both the snake and the grasshopper. Snakes slither when moving, so the implementation for the snake just prints out a message, slither to the coordinates. And for the grasshopper, the same thing applies. We print out a different message though, and grasshoppers hop around, so we use hop to the coordinates. Once we define the functions for both structs, we can say that the structs implement the move trait. So we know that the snake struct implements the move trait, so we have implement move trait for snake. And same for the grasshopper, implement move trait for grasshopper. Now that we have our trait implemented on snakes and grasshoppers, we can utilize it in a program. We have a function here that accepts a thing as a function parameter, and this thing has to implement the move trait. Within the function, all we do is call the move2 function that's defined on the move trait up here. And when we do so, whatever this thing happens to be, it'll call the specific functionality for that structure. In our program down here, we're creating a new snake and calling it Python. Once we call the makeMove function with the Python, control will go over here. Since snake implements the move trait, we can call the move2 function, and it's going to print out slither to 1, 1. And so this down here will be the output since we created a snake. So we have used the impl trait syntax before, and really what this is just a shorthand for generic syntax, which we'll be taking a look at next. Here is the full syntax for generic functions. It is a little verbose, but after writing a few generic functions, it becomes quick and easy. First, we have the fn keyword, followed by the name of the function as usual. Following the function name, we have some content here within angle braces. The content within these two braces define the generic trait bounds. These are also called generic constraints because we are constraining the function to only the traits that are specified within. The letter T here is just the name of the type we will use in the function parameters. By convention, generic types use a capital T, meaning some type T. Additional generic types are then U, V, W, etc. You can name these anything you like, but it can be hard to tell a generic type apart from a trait or structure, so usually you just want to stick with the capital T. Next, we have a colon followed by the name of a trait. We can put any trait here as a constraint, and whenever this generic type is utilized as the type in the function signature, the argument to the function must implement that trait. And if you need more than one generic type for a function, you can separate them with a comma. In this case, we have two generic types. We have a T and a U, And the t implements trait 1, and the u implements trait 2, and we have the comma to separate them. Now, after the trait bounds are defined, we can utilize them in the function parameters. All we need to do is, instead of specifying a type like string or u32, we just put one of the generic type names instead. In this case, we used t for param1 and u for param2. I'll go into detail how this will work with an example shortly, but there's one more thing we need to look at before we jump into that. There is actually another way to write a generic function, using what's called a where clause. The where clause allows you to cleanly specify multiple trait bounds without cluttering up the function signature. To use a where clause, we must declare the generic type names after the function name. In this case, we have a t and a u, so we have t, comma, u to declare our generic type names. Now, before the curly braces of the function, we need to include the where keyword. After the where keyword, we write out the generic type names and the traits that they are bound by, and each one is separated by a comma. In this case, we are using multiple trait bounds for each generic type. Here, type T is constrained by trait 1 and trait 2. U is constrained by trait 1, trait 2, and trait 3. We use the plus symbol to indicate that we want this particular trait to have both traits implemented. It is possible to use multiple traits with the plus symbol with the first syntax as well, but it becomes difficult to read almost immediately. So I generally prefer to use the second syntax if more than one trait or more than one generic parameter is required. The second syntax also makes it easier to update the traits, since each trait is on its own line along with the name of the generic type. Now that we've got the syntax covered, let's see it in action. Here is the makeMove function from earlier. The two functions are equivalent. The first uses the impl trait syntax, and the second uses the generic syntax. On the second syntax here, we defined a generic type t, followed by a colon, and finally the name of the trait that we created earlier, which was called move. In the function parameters, we set the thing to be of type t, which is our generic parameter t, and it must implement the move trait. What this does is tell the compiler that we are declaring a generic parameter called t. It must implement the move trait, and we are using this type here as the thing in our function. Here is the same function using a where clause and generics. We define the generic type t here and set the function parameter to use the generic type t. We then place the where keyword after the function parameters but before the curly braces. After the where keyword, we have our generic type t that we declared after the function name, followed by a colon, and ending with the name of the trait that we defined earlier, which is move. To put it another way, we are telling the compiler that we have a generic type t. We're using this generic type as a type for the function parameter, and this t must implement the trait move. So we have a type t where that type t implements the move trait. So far, I've shown you 3 different ways to use generics, so which syntax should you use and when? So the first syntax is the impl trait syntax, and it's fine if you just want to constrain the data to 1 or 2 traits, but can become difficult to read once you start adding additional function parameters. So you would want to use the impl trait syntax when you have a small number of traits and a small number of function parameters. The impl trait syntax is also great when you are first getting started with generics, since the syntax is clean and it follows the same pattern as implementing the trait itself, as we can see here. So if we implement the move trait for Grasshopper, we have impl move, and then the same thing in the function parameters, we have impl trait. So it follows the same pattern. The second syntax is commonly used with one or two generic types that only require one or two traits. Similar to the impl trait syntax, the generic portion of the signature can become cluttered if you have too many constraints, but the function parameters usually remain clean. I would normally use this syntax when I only have one or two traits and one or two generic types. The third syntax, although it takes a lot more vertical space, is usually always the easiest to read and modify once you have two or more traits or generic types. In our move trait example, using a generic function with the where clause would probably be more than needed, and one of the first two syntaxes would be more appropriate. However, the benefit of utilizing the where clause is when you want to update the trait bounds or easily be able to read the function signature. In the third example, we can see that we have two generic types. The parameters for the functions are very clear, and we can see the exact traits required for each generic type very clearly. The where clause is always more clear once you have multiple trait bounds on a single generic type, as we have in this example. One last thing we need to cover before finishing up. We have our trait from earlier that declares the move_to function. If we take a look at the generic function here, the makeMove function, we will see that it will call the move_to function that's defined on the trait. Later in the program code, we call the makeMove function using both a snake and a grasshopper. We know from previously that this should print out slither to 1, 1, followed by hop to 3, 3. Now, behind the scenes, our generic function actually gets expanded into these two functions. One of the function has a snake as a type, and the other one has a grasshopper as a type. So the generic function here that we set up earlier is really just a fancy way to create multiple regular functions that do the same things, just having different types. These individual functions here will have parameters that correspond to each type that you call the generic function with. We have two types in this program, so we have the snake and the grasshopper, and so we will get two copies of the makeMove function, as we see here. All of this happens as part of the compilation process and is called monomorphization, and this isn't something you need to manage on your own. It is a fully automatic process. However, it helps to understand how this works in order to have a better foundation for later lessons on dynamic dispatch and generic structures. To recap, generics let you write one function to work with multiple types of data. Generic functions are bound or constrained by the traits indicated in the generic definition section of the function. When you use generic functions, the function is only able to operate on data that implements the traits specified in the generic definition section. There are three syntaxes available to create generic functions. The first is impl trait. So this parameter can take any type that implements some trait. The second is generic syntax. A generic type T is constrained to a specific trait, and the function parameter must be a type T, meaning the argument passed to this function must implement this trait here. The third syntax utilizes the where clause. A generic type T is declared, and the function parameter is set up with generic type T, where this generic type T implements some trait.